There's this really beautiful idea in math, that many of the equations and graphs we spend our time with are just shadows of a more elegant, powerful, and higher dimensional mathematics. This higher dimensional mathematics has everything to do with the imaginary number I, the square root of -1. Extending polynomials like x squared plus 1 to include imaginary numbers is relatively straightforward. But there's one pair of functions, exponentials and logarithms, where the application of imaginary numbers is far less clear. 2 to the power of 3 means we should multiply 2 by itself 3 times. But what could it possibly mean to raise 2 to the power of the square root of -1? In the early 1700s, disagreements over these questions threatened the very foundations of mathematical analysis, until Leonard Euler stepped in with a solution so surprising and elegant that it's often called the most beautiful equation in math. This video is sponsored by me. I've written a whole book on imaginary numbers. It's coming out later this year. You can pre-order a copy using the link in the description below. On March 16, 1712, Gottfried Wilhelm Leibniz, co-founder of calculus, sent this letter to the mathematician Johann Bernoulli, where he claimed that it was impossible to take the logarithm of a negative number. As Leibniz would detail in a later letter to Bernoulli, logs are just another way to write exponents, and simply don't make sense for negatives. Log base 2 of 8 is 3, because 2 to the third power is 8. Log base 2 of 1 is 0, because 2 to the power of 0 is 1. The reason 2 to the 0 is 1, and not 0 or something else, is that this definition preserves an important property of exponents and logarithms. When we multiply two terms with the same base, their powers add. 2 squared times 2 cubed results in 5 total multiplications of 2, or 2 to the 5th. Defining 2 to the 0 as 1 preserves this property. 2 to the 3 plus 0 equals 2 to the third times 2 to the 0, if and only if we define 2 to the 0 as 1. As we'll see, finding mathematically consistent ways to handle logs and powers of various types of numbers is critical to making sense of Euler's approach. Finding a sensible definition for logarithms of fractions between 0 and 1 is also relatively straightforward. Dividing exponential terms with the same base is equivalent to subtracting their exponents. 2 cubed divided by 2 squared is equal to 2 to the 3 minus 2. This means that 2 to the minus 2 on its own must equal 1 over 2 squared. This is how we arrive at the logarithms of fractions. The log base 2 of 1/4 is equal to -2, because 2 to the -2 is 1/4. Note that we've broken away from the simple definition of integer exponents, where an exponent of n means we multiply a number by itself n times. This doesn't make sense for negative exponents. However, our fractional definition nicely preserves our properties. And when we plot the value of log base 2 for numbers greater than 1 for 1 and for fractions, we get a nice continuous curve. Now, when we finally reach the logarithms of negatives, as Leibniz claims, we basically run out of options. What power of 2 would result in -1? Clearly, positive numbers 0 and negatives will not work. In a response letter a few weeks later, Bernoulli flatly rejects Leibniz's claim. Bernoulli argues that since the derivatives of log x and log of negative x both evaluate to 1 over x, log of x and log of negative x are equal. This would mean that the log function wasn't just one curve, but actually had a positive and negative branch that are symmetric across the y-axis. And the log of -1 just equals the log of 1, so 0. Leibniz was not convinced, and the mathematicians went back and forth for over a year, without making progress towards a meaningful resolution. When Leonard Euler, a student of Bernoulli, picked up this still unresolved problem a few decades later, he wrote that not finding a reconciliation would be an indelible stain on analysis. At this point, calculus and analysis were still only 5 or 6 decades old, and relied on some serious hand-waving to handle the infinitely large and infinitely small quantities required. Euler speculated that other mathematicians had encountered the same difficulties with logarithms, but had not published out of fear of breaking this new branch of math without being able to fix it. In an incredible 13-page paper written in 1747, Euler points out logical flaws with the solutions of both Bernoulli and Leibniz, and lays out an unbelievably elegant solution that remains largely unchanged today. First, Euler demolishes his teacher Bernoulli's theory that log of x equals log of negative x. Euler argues that just because log x and log of negative x have the same derivative, this does not mean that the functions themselves are equal. The same faulty logic can be used to show that log of 2x equals log of x, which is clearly false. From here, Euler draws on an example from Bernoulli himself to show that Leibniz is partially correct. In 1702, while investigating the areas of sectors of circles, Bernoulli got stuck on this difficult integral that computes the area of a sector as a function of the position xy on the corner of the sector. Bernoulli realized that if he effectively pulled a square root of -1 out of his expression, he was able to evaluate the integral. The result is a fairly complex expression for the area of the sector, involving I and a logarithm. Euler showed that if he chose the point xy to be 0, 1, Bernoulli's equation would simplify into the logarithm of -1 divided by 4i. Euler argued that since the area of the sector was clearly a real quantity, that the I in the denominator would have to cancel with an I in the numerator, meaning that the log of -1 had to be imaginary. However, just declaring that logarithms of negative numbers are imaginary does not fix the problem, and as Euler goes on to show, it leads to a new set of contradictions. A key property of logarithms is that raising the argument of a logarithm to a power is equivalent to multiplying the logarithm by the power. The log of 2 cubed is equal to 3 times the log of 2. Having established that the logarithm of -1 is imaginary, we can write log of -1 equals b times I, where b is some real number multiple of I. Euler then considered the case where the -1 inside the logarithm is raised to the power of 2. Applying our property, this should be equal to 2 times the logarithm of -1, or 2bi. However, since -1 squared is just 1, and we know that the logarithm of 1 is 0, it also appears that the log of -1 squared is equal to 0, which we just showed cannot be the case. Euler was stumped. Fully appreciating that the foundations of calculus were at stake, Euler wrote that he was tormented by these difficulties, and that for a long time it seemed impossible to rescue the truth. Finally, Euler found a way forward. What if both answers, 0 and 2bi, were correct? What if logarithms didn't have a single answer, but many, maybe even an infinite number of solutions? To see how this is possible, we need to return to the very first question we considered. What does it mean to raise a number to the power of the square root of -1? Although Euler's solution to this problem is incredibly elegant, his path to the solution is not the most intuitive. Euler put a huge amount of trust into his symbols, and was absolutely masterful at finding creative ways of manipulating equations. Euler's mathematical style, and a general mistrust among mathematicians of imaginary numbers, meant that although Euler's 1747 solution is essentially correct by modern standards, it would take over 50 years, well after Euler's death, to be widely accepted. A key factor to the broader acceptance of Euler's solution was the development of more visual ways of thinking about imaginary numbers. Let's use this more visual, intuitive approach to arrive at Euler's answer, and see how he saved calculus. Imaginary numbers are typically used as parts of complex numbers, which have real and imaginary components, often written as a plus bi. We can visualize complex numbers as points on the complex plane, where the real axis is horizontal and the imaginary axis is vertical. We can multiply complex numbers together using the distributive property, and the product of two complex numbers is generally another complex number. A notable exception is when we multiply a complex number by its conjugate. This just means flipping the sign of the imaginary terms. When we work out the multiplication in this case, the imaginary parts will cancel. Taking the square root of this result gives the distance between the number and the origin on the complex plane, also known as the magnitude of the number. Finally, it's very helpful sometimes to express complex numbers in polar form, where instead of writing the real and imaginary parts, we give the magnitude and the angle measured from the x-axis. Multiplying complex numbers in polar form is particularly useful, because it turns out that all the distributive property algebra is completely equivalent to multiplying together the magnitudes and adding the angles of our numbers. So when we multiply two complex numbers together, their magnitudes multiply and their angles add. Now, returning to our problem of what it means to raise a number to an imaginary power, let's consider 2 to the power of some number b times I. An easy operation we can try right away is multiplying this expression by its complex conjugate, 2 to the minus bi, which should give us the distance squared between the origin and 2bi. Following our additive exponent property, the exponents cancel, and we're left with 2 to the 0 equals 1. This is a powerful result. Since our result is a constant that doesn't depend on b, It means that the magnitude or distance from the origin of 2 to the bi is constant, so 2 to the bi must fall somewhere on a circle of radius 1. Perhaps most surprising here is that unlike functions of real exponents, which grow and grow as their arguments increase, functions with imaginary exponents are completely confined to the unit circle. As we'll see, this has everything to do with Euler's assertion that logarithms have an infinite number of solutions. Now, the missing piece of the puzzle, of course, is where exactly does 2 to the bi fall on the unit circle? We now know that the magnitude of 2 to the bi is 1, but what is its angle? To be more mathematically precise, we're saying that 2 to the bi equals some point on the unit circle. Let's say it's at angle theta. So we can write it as a complex number with cosine theta for the real part and sine theta for the imaginary part. Now, can we figure out how b and theta are connected? If we plug in b equals 1, what happens to theta? If we can figure this out, we will have completely solved our problem. To get to the bottom of this, we need to go one level deeper into how exponential functions really work. As we've seen, it's relatively straightforward to make sense of integer exponents, regardless of if these exponents are positive, 0, or even negative. But what about fractional or decimal exponents? Simple fractional exponents like x to the 1/2 are pretty straightforward. By preserving the property that powers of powers multiply, we can show that x to the 1/2 is equivalent to the square root of x. But what about more complicated powers like 0.587? Sure, you can plug this into your calculator, but how does it really work? The first person to really attack this problem was Henry Briggs in 1617, when constructing his incredibly prolific tables of base 10 logarithms. Briggs found a clever computational approach that works by basically zooming way in on an exponential curve until it looks like a straight line. Starting with an x value of 1, for example, we can zoom into our curve by dividing x by 2 and computing the corresponding y value. In this case, 2 to the power of 1/2 equals the square root of 2, or roughly 1.414. Repeating this operation again to zoom in further, we reach x equals 1/4 and y equals the square root of the square root of 2, which is equivalent to the 4th root of 2, or about 1.189. After zooming in more and more, Briggs remarkably took 54 successive square roots to the 33rd decimal place. We reach a tiny neighborhood, where 2 to the x is very nearly equal to 1 plus alpha times x. This is the equation for a straight line in this neighborhood with a slope of alpha. Briggs used a slightly different formulation, but in our example here, the slope alpha comes out to about 0.693. So when x is close to 0, 2 to the x is very nearly equal to 1 plus 0.693 times x. We can now use this fact, as Briggs did, to solve arbitrary logarithm or exponential problems, like 2 to the power of 0.587. Taking our x starting value as 0.587, we first map to our tiny neighborhood by either taking successive divisions by 2 as Briggs did, or we can go in one big step. To zoom in by a factor of 1,000, for example, we divide 0.587 by 1,000, so 0.000587. Assuming we've made it to our tiny neighborhood, we can now find 2 to the power of 0.000587, using our simple linear formula. So 1 plus 0.693 times 0.000587 gives 1.000406791. Now that we know 2 to the power of 0.000587, we can zoom back out to get our final answer by raising this result to the power of 1,000, computing about 1.5019. Plugging this problem into a modern calculator gives an answer a little closer to 1.502. This is just because a factor of 1,000 isn't really zooming in that far. If we zoom in by a factor of 1,000,000 instead, our answers match to the 6th decimal place. We can wrap up what we're doing here nicely into a single equation. 2 to the x approximately equals our linear equation, 1 plus 0.693 times x, divided by our zooming in factor n, all to the power of n to zoom back out. The bigger n is, the more precise our answer is. Injecting a little calculus, 2 to the x is exactly equal to the limit as n approaches infinity of our expression. This is still not quite correct though, because we rounded the slope of our line alpha to 0.693. The way this is typically handled is to make the slope term equal to 1 by changing our base. If we define a new variable, x equals z divided by 0.693 and substitute, we're left with a simpler expression on the right and a new base of 2 to the power of 1 over 0.693 on the left. Given more decimals of precision for alpha, our new base evaluates to 2.71828, also known as the mathematical constant e. Putting all of this together, we have an equation that is often used as the definition of the exponential function. E to the z equals the limit as n approaches infinity of 1 plus z over n all to the power of n. This equation elegantly describes the zooming in, linearizing, and zooming out procedure that Henry Briggs developed to compute the exponents and logarithms of decimals and fractions. Now that we have a deeper foundation for what an exponential function really is, we're finally ready to make our final attack on imaginary exponents. The key idea from here on out is figuring out if Briggs' infinite zooming in definition of exponentials works with imaginary numbers. And if so, where on the unit circle a number to a specific imaginary power will land. So what happens if we plug in the square root of -1 into Briggs' equation? Can we trust the results even though Briggs' equation was derived using real numbers? What does all of this mean geometrically? Let's plug in z equals I and temporarily drop the limit and use a smaller value of n, let's say 6. This will reduce the precision of our result, but the intuition should still hold. So we have e to the power of I approximately equals 1 plus I over 6 all to the 6th power. 1 plus I over 6 is not too tricky to think about. It's just a complex number with a real part of 1 and an imaginary part of 1 over 6. Briggs' formula is telling us to multiply this complex number by itself 6 times. Performing the first multiplication, we get 35 over 36 plus I over 3. The polar form of complex numbers is helpful here as we continue multiplying. We can write 1 plus I over 6 as the complex number with a magnitude of 1.014 and an angle of 9.46 degrees. Since multiplying complex numbers in polar form is just a matter of multiplying magnitudes and adding angles, we can jump to our final answer by raising 1.014 to the 6th power and multiplying 9.46 degrees by 6, giving a final magnitude of 1.086 and an angle of 56.774 degrees. Note that our answer is not quite on the unit circle as expected, but this is just because we're using a fairly small value for n. If, for example, we bump into 1,000, we land much closer to the unit circle. So could this result be correct? Is it consistent with all the nice exponential and logarithm properties that we've seen thus far? And can it help us figure out the relationship between b and theta in the unit circle equation we derived earlier for 2 to the power of bi? Let's go ahead and rewrite this equation in terms of the base e to better line up with Briggs' equation. Since b is just an arbitrary constant, we can introduce a new variable b is equal to c divided by 0.693, just as we did with Briggs' equation. Substituting, we can rewrite our equation as e to the ci is equal to cosine theta plus I sine theta. And our job now is to find the connection between c and theta. When we plugged I into Briggs' equation, effectively using a c value of 1, and used an n value of 1,000, our result was a complex number with a magnitude of 1.0005 and an angle of 57.296 degrees. This angle should be equivalent to the theta value in our cosine plus I sine theta equation, when c equals 1. So when c equals 1, theta equals about 57.296 degrees. Let's plug in more values of c into Briggs' equation and see how theta changes. Plugging in the values 0 through 5 for c, a pattern emerges for theta, with theta increasing by a constant value of about 57.296 degrees for each increase of c by 1. So this result is telling us that if we raise e to the imaginary powers of I, 2i, 3i, and so on, our answer moves around the unit circle in equal steps of about 57.296 degrees. Now, if we make a small change and measure theta in radians instead of degrees, we see something truly remarkable. Each increase of c by 1 moves theta by 180 divided by pi, or exactly 1 radian. So if we measure theta in radians instead of in degrees, the value we've been calling c is exactly equal to theta. Finally, we've arrived at Euler's incredible formula. E to the power of I theta equals cosine of theta plus I sine theta. Now, before we celebrate too much, we never really checked that Briggs' formula makes sense when our inputs are imaginary. After all, Briggs developed his formula by zooming in on a very real exponential curve that has nothing to do with imaginary numbers. When we plugged in I into Briggs' formula using n equals 6, we saw that visually this looks like 6 thin triangles stacked together to form an overall angle. Each triangle has an angle of 9.46 degrees. And when we multiply this number by itself 6 times, these angles are added together to produce a final angle of about 57 degrees or 1 radian. As we increase in, we get more and thinner triangles, and a more accurate estimate of e to the power of I. Considering our first thin triangle for a moment, if n is 100 for example, then the base of our triangle is equal to 1, the real part of 1 plus I over 100. And the height of our triangle is equal to the imaginary part, so 1 over 100. Now, where it gets interesting is if we consider the connection between the small angle of this thin triangle, let's call it delta, and the height of our triangle. From trigonometry, we know that the tangent of delta equals the height of our triangle divided by its base. So 1 over 100 divided by 1. Now, just like the exponential function, it turns out that if we zoom way into a tangent function, it also looks just like a straight line. And the slope of the tangent function in the neighborhood close to 0 turns out to just equal 1. So for small values of delta, the tangent of delta just equals delta. What this means for our thin triangle is that as n approaches infinity, the height of our little triangle exactly equals our angle delta when delta is expressed in radians. Now, fitting all the pieces together here, taking some imaginary exponent ci, Briggs' formula tells us to divide c by n. This effectively gives us a thin triangle with a height of c over n. And if n is big enough, the small angle of this triangle is equal to c over n radians. Now, Briggs' formula tells us to multiply this triangle by itself n times, which using the polar form of complex numbers means we add our angle delta up n times, which gives a final angle of c over n times n, or just c. This is why c is equal to our final angle theta expressed in radians. Just as Briggs' formula linearized the exponential curve for real exponents, it's remarkably able to work in a similar way for imaginary exponents. In the imaginary case, this happens in the 2D space of the complex plane, and it works out because we can linearize the tangent function for very small triangles. And because multiplying all these little complex numbers together results in rotation on the complex plane, we end up with rotation instead of growth. Now that we have Euler's formula, we can finally see how he saved calculus. We left off with Euler arguing that both Leibniz and Bernoulli were wrong, and that the log of -1 has more than one correct answer. If we take the natural log of both sides of Euler's formula, we're left with I times theta is equal to the natural log of cosine theta plus I sine theta. Euler was interested in the case where the argument of the logarithm is -1. This will happen whenever the cosine term equals -1 and the sine term is 0. On the complex plane at the point -1, 0 on our unit circle. A theta value of pi radians will work here, but so will -pi, 3pi, -3pi, and so on. So the logarithm of -1 is equal to all odd multiples of pi I. This is precisely what Euler means when he says that logs have an infinite number of solutions. Euler's paradox about the logarithm of -1 squared now has a straightforward solution. If we drop the 2 down, this means multiplying all the solutions of log of -1 by 2. So -6 pi I, -2 pi I, 2 pi I, and so on. Now, the contradiction came up when we squared the -1 first, instead of dropping it down. This gives us the log of 1. Using Euler's formula, the log of 1 will happen when the cosine term is equal to 1, and the sine term is equal to 0. So at angles of 0, 2 pi, -2 pi, and so on. As Euler points out in his paper, the solutions to 2 times the log of -1 are visibly contained in the solutions to the log of 1. This fact, along with a number of other impressive results, convinced Euler that defining logarithms and exponentials in this way would save the foundations of calculus. Euler's approach was highly controversial at the time, but would eventually gain acceptance. Personally, I don't think it's surprising that Euler's formula and his approach to logarithms was so controversial. If we just look at Euler's formula, it's pretty absurd. To the right of the equal sign, we have cosine and sine waves from trigonometry. To the left, we have e raised to a power, which typically means exponential growth. The wild card here is of course the imaginary unit I, which as we've seen is almost as if by magic, turning exponential growth into periodic wave-like motions. We began our discussion with the idea that many of the equations and graphs we spend our time with are just shadows of a more elegant, powerful, and higher dimensional mathematics. The deep connection between exponentials on one hand and sine and cosine on the other is perhaps the most stunning example of this in mathematics. If we take a polynomial function like x squared plus 1, expand its inputs and outputs to be complex numbers, and visualize one of these imaginary parts of the function as the height of a surface above the real plane, we get these cool paraboloid shapes. Incredible, but perhaps not a surprising extension of parabolas to complex numbers. But when we take the familiar exponential growth function of real numbers and expand its input and outputs to be complex numbers using Euler's formula, the surface that emerges incredibly is shaped exactly like sine and cosine waves. The projection of this surface in one direction is our familiar exponential curve, and in the other direction are cosine and sine waves. And this structure is not some invention. It literally falls out of our familiar rules of algebra, carefully applied to imaginary numbers. All of these pieces of mathematics somehow fit together perfectly into a form we could have never imagined, making Euler's formula the most beautiful equation in mathematics. If you want to get deeper into imaginary numbers, I really think you'll like my book. Way back in 2016, I made a massive 13-part YouTube series on imaginary numbers. It's such an incredible topic. I released an early version of this book back then, and I'm now in the process of revising, correcting, and significantly expanding it. My goal is to create the best book out there on imaginary numbers. High-quality hardcover printed books will start shipping later this year. You can pre-order a copy today at the link in the description below. And your order includes a free PDF copy of the 2016 version that you can download today. I also made a poster version of the table from this video that walks through the incredible path to Euler's formula. This is the first dark mode poster I've done, and I'm super happy with the look and feel. This poster is a great visual explanation of the path we took here to get to Euler's formula, and I also just think it looks cool. You'll find all of this and more in the Welch Labs store.